Good day, I'm Yasin. I'm from Group 2, and our project is entitled Instrumental Plantarflexed Ankle Foot Orthosis with Real-Time Biofeedback. This project focuses on developing a smart orthotic device that combines wearable sensors and biofeedback technology to assist individuals with equine deformity during rehabilitation. Firstly, I'm Yasin. Then here is Avish, Kisendra, and Ashi.
Hi everyone, my name is Asri Melisande and today I will explain about the introduction, problem statement, and objectives. Walking is a fundamental daily activity that requires coordinated movement of the hips, knees, ankles, and feet. During a normal gait cycle, the foot progresses through several passes, including heel streak, stage, push off, and swing pace. During the swing pace, the foot must achieve sufficient ground clearance to avoid contact with the ground before the next step is taken. Proper ankle and foot positioning are essential for maintaining balance, stability, and walking efficiently. Any disruption to this movement can negatively affect mobility and increase the risk of falls. In recent years, wearable gait monitoring technologies has become increasingly important in rehabilitation because they provide a convenient and portable method for continuously monitoring gait performance outside laboratory environments. Equinus deformity is a condition characterized by limited ankle dorsiflexion and excessive plantar flexion, causing the foot to remain pointed downward. Individuals with equine deformity often walk on their toes instead of following normal heel-to-toe gait pattern. This abnormal foot posture prevents proper heel contact during the initial pace of walking and reduces to clearance during the swing pace. As a result, individuals are more likely to experience toe dredging, tripping, and falling. These gait abnormalities can significantly affect mobility, balance, walking confidence, and overall rehabilitation outcomes. Although conventional ankle-foot orthoses or AFOs can provide mechanical support and improve foot alignment, they are passive devices that cannot monitor gait performance or provide real-time feedback when unsafe gait patterns occur. Next slide. The main objective of this project is to design an instrumented plantar flexed ankle foot orthosis with real-time biofeedback to monitor gait and improve walking safety in patients with equinus deformity. The specific objectives are divided into 6 parts. First, AFO design to support plantar flexed foot posture. Second, pressure detection using FSR sensors at the heel and forefoot. Third, foot angle monitoring using an MPU 6050 IMU to detect excessive plantar flexion. Fourth, real-time gait monitoring using Arduino Uno. Fifth, audio biofeedback using a buzzer during unsafe plantar flexion. Lastly, walking safety to improve awareness and reduce toe drag risk.
Previous studies have shown that conventional gait analysis methods such as motion capture system and force-based provide accurate measurements but require specialized laboratory facilities and are not suitable for continuous daily monitoring. To overcome these limitations, wearable sensors have been widely adopted in gait monitoring applications. Initial measurement units or IMUs can measure lower limb movement and foot orientation while force-sensitive resistor can detect plantar pressure and identify gait phases such as heel strike and toe up. Research has also demonstrated that biofeedback system can improve gait awareness by providing immediate information regarding movement errors. Real-time auditory feedback encourages users to make corrective actions and support motor learning during rehabilitation. This finding motivates the development of our instrument AFO system that combines FSR sensors, IMU sensors, and real-time biofeedback into a single rehabilitation device.
So in this prototype, for the mechanical part, the hardware component that was used is the solid AFO. To improve the plantar flexion AFO condition, we add heel lift beneath the AFO's heel. For the mechanical part, we use FSR that were located at the AFO's forefoot and heel, and we also use inertial measurement unit IMU, MPU 6050. The data obtained will be processed by the Arduino Uno, and this prototype's power will be supplied by rechargeable power bank.
This design focuses on developing a real-time gate monitoring and biofeedback system integrated into a AFO, solid AFO. The main objective is to detect the gate events such as heel strike, forefoot contact, and the swing phase in order to identify unsafe walking patterns and provide immediate corrective feedback. From a mechanical perspective, we use a rigid polypropylene AFO to maintain proper ankle alignment while allowing controlled plantar flexion for managing equinus deformity. To preserve structural integrity, no permanent modifications are allowed and all added components are attached using non-invasive methods. Electrically, the system uses lightweight components powered by 3.7-volt battery. A minimum sampling rate of 50 Hz ensures accurate gate detection, while clear audio feedback enables intuitive patient response. This design enhances an existing solid AFO by adding an external sensing system for real-time gait monitoring. Plantar pressure sensors placed at the heel and forefoot detect foot ground contact and load distribution, while an IMU attached on the calf tracks lower leg motion and confirm the swing phase. Sensor data is processed by an Arduino Uno in real time and compared with predefined safety limits. When unsafe gait patterns are detected, an active buzzer provides immediate audio feedback. This allows the patient to correct their walking pattern and reduce the risk of trips or falls. Sensor placement is crucial for accurate gait monitoring. The heel FSR is placed under the heel to detect heel strike and identify the start of the stance phase. The forefoot FSR is positioned beneath the metatarsal region to monitor push-off forces and detect toe drag or abnormal loading. The IMU is attached on the calf shell of the AFO to minimize motion artifact and accurately track lower leg movement. All sensors are attached using non-destructive methods to ensure comfort and reliability.
Hello Doctor, my name is Muhammad Darwish and I will present our finalized instrumented plantarflexion AFO prototype developed in this project. The slide shows the prototype from the front, side and back views. Starting with the front view, the placement of the FSR sensor beneath the foot can be observed together with the securing strap used to maintain proper foot positioning within the orthosis. Moving to the side view, the overall profile of the AFO can be seen, including the alignment between the foot section and lower leg section. The rechargeable power bank used to supply power to the system is also visible from this view. Finally, the back view highlights the electronic integration of the prototype, including the heel extension modification, Arduino and breadboard assembly, wire routing, and sensor connection. We will look to software calibration and warning implementation used in the development of the prototype. First, a calibration program was developed to obtain real-time foot angle measurement from the MPU 6050 sensor. During the calibration, the FO was connected to a laptop and the measure angle values were displayed through the serial monitor. The initial record angle was approximately negative 78.32 degrees. It was observed that the angle value decreased as the foot moved further into plantar flexion. Based on this measurement, a warning threshold of negative 92 degrees was selected. The selected threshold was then implemented in the final warning program. As shown in the warning detection logic, the piezo buzzer is activated only when two conditions are met. The system must detect swing phase and the measured foot angle must fall below the 92 degrees. This implementation allows the prototype to provide auditory feedback when excessive plantar flexion is detected during walking. Next, I will show you to our prototype video demonstration. Next, we will look to system gate response result. Based on the prototype demonstration shown earlier, The observed system response are summarized in this table. In the first case, when the user is in the stun phase, both FSR sensor detect weight bearing and the buzzer remains turned off regardless of the measure foot angle. In the second case, during swing phase, when the measure foot angle remains above the warning threshold of negative 92 degrees, the foot is considered to be in normal clearance position and no warning is generated. In the third case, when excessive plantar flexion occurs during swing phase and the measure foot angle falls below the negative 92 degrees, the piezo buzzer is activated to provide an auditory warning.
Then the design evaluation was conducted to determine whether the prototype achieved the intended project objective. First, the FSR sensor successfully detected plantar pressure at the heel and forefoot regions, allowing the system to differentiate between stance and swing phase. Second, the IMU sensor successfully measured foot orientation and monitor plantar flexion angle during walking. Through calibration testing, a warning threshold of negative 92 degrees was established and incorporated into the system. Third, the auditory feedback system successfully detected when excessive plantar flexion was detected during the swing phase, providing immediate feedback to the user. In addition, the heel lift modification incorporated into the AFO accommodated the plantar flex foot posture and supported gradual gait retraining. To conclude, the prototype successfully achieved the project objective and demonstrated the feasibility of the integrating wearable sensors and biofeedback technology into an orthotic rehabilitation device. However, the prototype achieved its objective. Several limitations were identified during development and testing. First, gait characteristics may change when users perform dual task activities such as carrying objects or using a mobile device while walking. This variation may affect ankle measurements and warning accuracy. Second, the weight of the electric components may slightly influence natural gait patterns and reduce user comfort during prolonged use. The operating duration of the system is limited by battery capacity, and also the current prototype does not include data storage or remote monitoring capabilities. Future improvement may include the development of a smartphone application that allows real-time visualization, data logging, and rehabilitation progress tracking. Wireless communication technologies such as Bluetooth could also be incorporated. In addition, miniaturized electronics and custom printed circuit boards could also improve portability and user comfort. In conclusion, this project successfully developed an instrumental Plantarflex ankle foot orthosis with real-time biofeedback for individuals with equinus deformity. The system integrated FSR sensors, IMU sensors, and Arduino Uno microcontroller and auditory feedback mechanism to monitor gait performance and detect excessive plantar flexion during the swing phase. Functional testing demonstrated that the prototype was capable for distinguish between gait phases and providing appropriate warnings when unsafe gait conditions were detected. The inclusion of a heel lift modification further supported gait rehabilitation by accommodating the plantar posture and encouraging gradual gait progression. Hence, the project demonstrates the feasibility of combining wearable sensors technology with orthotic rehabilitation and provides a foundation for future development of smart AFO system and at improving gait safety and restoring normal walking patterns. Thank you for your attention. That's all from my group.